Okay, so this is the recording of section 6.3. You guys should probably be taking some notes on this. We've got today and Tuesday. Remember, our test is Wednesday. I'll put up the homework assignments today before I go home. This is 6.3, properties of the trig functions. 6.3, properties of the trig functions. And if this class is anything like my A period class, we'll get the sine and cosine today, and we'll keep the tangent and the reciprocal functions for Tuesday. Okay, but if you know sine and cosine really well, the rest of them are super easy. In fact, if you look at the big scheme of things, if you know sine, cosine, and tangent, and just a little bit about secant and cosecant and cotangent, then you'll be okay. Okay, so let's really focus on sine and cosine today. If we have time, we'll do tangent as well. What do we mean by properties? Well, if you go back to your library function, let's suppose we have this function. I'll call it theta. It's a function of theta, and we'll do the sine of theta. So what do we mean by properties? Well, things like domain and range. So you got to know that. It would be nice to know the zeros. We're not going to get into the zeros today, probably not till section 6.4. But you should know whether this is even or odd. And the other thing we'll talk about for these trig functions is something called the period. These functions have a tendency to repeat. So if we figure this out for the sine, then we should be okay for the other ones as well. Okay, so what do we mean by domain and range? Well, on your last chapter test, I actually gave you a picture of a sine wave, and it looked like this. It was a wave that continued like that. And if I told you this high spot was at 1 and this low spot was at -1, and this now, I guess I should call it the theta axis because that's my independent variable, right? That's this. You can think x if you want. And my dependent variable is the sine of theta. Okay, and we just looked at the picture, and that's all. And I said, what is the domain of this graph? You know, what are the allowable values going this way? How far out does it go? Infinity. Okay, so this is going to be all reals, or if you want, infinity, negative infinity to infinity. You can put any angle you want into this trig function. I got my calculator here. I happen to be in radian mode. That's the default. I can put sine of 1,027 radians in there, and it spits out a number. It doesn't matter what angle I put in there, right? I can put negative angles in there, the sine of negative 23.56 radians, and it spits out a number. Wow, that's almost right on top of 1. By the way, the sine, as we travel around the circle, right, wasn't the sine the y-coordinate? Right? The sine was the y-coordinate. So, I mean, if we're thinking unit circle, and this is the unit circle going around and around and around, and I have a dot, a point. Now, your quiz was give me the coordinates of some of the points. This point must be really close to the top, right? So maybe it's just to the right or just to the left. I don't know, but I know the y-coordinate's almost 1. Right? I just threw that number out there, negative 23.56. By the way, if I did the cosine of the same angle, and we're focusing on sine right now, but the fact that this was so close to 1 is sort of cool, negative 23.56. If I did the cosine of that, it comes up to be a negative number. What quadrant am I in? Oh, I know it's near the top of the circle. Is it the first quadrant or the second quadrant? It's got to be the second quadrant. How do you know? What do you mean? Okay, so it's, but how do you know it's Q2? You mean the x-coordinate? Yeah, right. So the cosine is a negative number and the sine was a positive number, right? So we must be over here somewhere. So this point, you know, it could have been there if they were both positive, but we know the x-coordinate's negative. So sure enough, that point is lying in the second quadrant. Now, I don't know negative 23 radians. Golly Moses. It's sort of hard to figure out. Can we do it in degrees? How would you convert that to degrees? I mean, this is sort of a review at this point. Negative 23.56. What do I have to multiply it by? No. No. What do I multiply it by? 1 of what form? No. 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 What do I multiply? I multiply by 1 of what form? What do I multiply it by? 1. What form do I use? No, 180 is not pi. 180 is 180. Pi is about 3. 180 is not 3. Aha! Degrees. Yes? Okay. So let's multiply this by, now give it to me, Mihalik. No. No. Yes. Pi divided by 180 degrees, right? Golly Moses. Got to put the degree symbol in. There. Now it will work. Right? So this is how many degrees it is. Oh, sorry. I already had radians, right? So I wanted to turn it 2 degrees. Good. Thank you. So 180 degrees divided by pi. Boy, it's like pulling teeth. Okay. Golly day, it's still 1, right? That is the number 1. So when I multiply by 1, I still get the same, well, that's the whole idea. Look at this. Negative 23.56, right? This is in radians. I want to turn it into degrees. That's 180 degrees over pi. I guess I really can't use the calculator very easily, right? I do know that this is going to end up with degrees, yes? Okay, so let's see if we can throw that in here. Negative 23.56 times 180 divided by pi. Divided by pi. And it's that many degrees. Wow, minus 134.9.888565. Now we were talking these goofy snowboard turns the other day, right? So let's think degrees for a minute. 1 full rotation, think degrees, 360, right? 2 full rotations. We've committed a foul of part 2, so that's a 720. By the way, in sailing, if you foul somebody, you can continue racing if you do 2 complete circles, a 720-degree turn. Okay, so we got 360 degrees. We got 720 degrees. What's 3 full rotations? What would we have to add? Okay, so we add 360, so that's up to 1080, right? And another rotation after that? 1440, you're adding 360? So 1440. Okay. This is a negative rotation. So where the heck does this fall in the scheme of things? We know we're supposed to be near the top of the circle, right? That's what it says. If we looked at the, and go back and find wherever this was, there was the cosine, and there was the sine, if I can find it. You know, your calculator stores stuff. I can go back and find that other command. There it was. Okay, really close to the top of the circle. By the way, when somebody leaves a calculator laying around and it doesn't have their name on it, I just do second enter, second enter. I can see the stuff they're doing. If they're doing, you know, trig stuff, I say it's either my class or Mr. Wood's class. If it's calculus stuff, it's either Mr. Nelson's class or my class. Right? If it's basic algebra stuff, you know, it could be an algebra class just by seeing the commands that you're doing. If it's science stuff, oh, well, that's a chemistry thing. I can go give it to a chemistry teacher. Right? Okay. So at any rate, this rotation, this minus 1,349 degrees is going to end up. So that's going to come into play when we talk about periods. So we may hold this one in abeyance just for a minute and come back to it. At any rate, we're doing domain and range. What's the range of this red mark, this red wave? Okay, so how do you write that in interval notation? Good, good. Okay, so all the numbers between 1 and -1. Occasionally you will get up to 1, right? So if I put in what is the sine of, and I happen to put in the number 100.5 pi, I throw that in there, 100.5 pi's, it comes out to be 1. It's like, oh, okay, so I can actually get to the top of the circle by doing 100.5 pi's, okay? And I can also get to the bottom of the circle. If I did 101.5 pi's, I get to the bottom of the circle. That's a -1. Most of the time, if you just throw a random number in there, you're going to get some number between 1 and -1. This wave oscillates. Okay. How about even odd? Is this even or odd? That was one of the questions on your last test. It is odd, so it's symmetric about the origin, right? So think of the other odd functions like y equals x cubed, yeah, or anything like that. Go back to the unit circle for a minute. If we had our unit circle and we had a point on the circle and I put it somewhere, so let's say I go to there and I look at this angle and I call that angle theta. This is theta. Okay. What does a negative theta look like? Goes clockwise, actually. Goes the other way, right? Negative angles. So this angle right now is negative theta. And I have this point down here. Now talk to me about the coordinates of these two blue dots. Are they the same? No, they're not the same. But are the x-coordinates the same? Yeah? Okay. So as we look at these guys, we go, you know, this has an x and a y, and this has an x, but the y is the opposite of that y, right? Down on the bottom. Okay. If I said what was the sine of theta and the sine of negative theta, are those two things the same? Are they the same? Look at the picture. The sine's the same. What was the sine? We did that yesterday. Sine of a angle was that the x or the y? It was the y. Are the y coordinates the same? No, they're opposite, aren't they? Yeah. Sine is the opposite. Back when we did even and odds, now I wasn't here, that was Dr. Hebert, but the definition of an odd function, the definition was f of x is the opposite of f of negative x. And you might want to go back in your text and find that. Maybe I can find a reference this weekend. Whether you put the minus sign there or there, it doesn't much matter. Okay, so f is the opposite, f of x is the opposite of f of minus x. And you're seeing that. These two y coordinates are different. So sure enough, the sine is an odd function. And since we're here, we might as well talk about the cosine. Is the cosine of an angle the same, he puts a question mark there, of the cosine of negative theta? Those are the same, right? Exactly the same x-coordinate? Yeah. So if f of x was equal to f of minus x, that's an even function. Somebody give me an even function, any even, not a trig function, even function. Y equals x squared. This morning somebody said the absolute value of x. X squared is fine too. If we have y equals x squared, and we know what the picture looks like, it's this good old parabola, and we went over here a distance called x, and we went up a certain amount, and we went the same distance going this way, and we go up, don't we go up the same amount? I mean, you try putting numbers in. If this is 3, this is 9. If this is negative 3, this is 9. Right? So f of negative x is exactly the same as f of x. That's the definition of an even function. And in fact, when we look at the cosine, cosines will be even. Sines are odd. Okay, we're trying to get all the properties of the sine function. Let's see what we got so far. We've got the sine of theta. Yeah, domain, let's say, I don't know, let's call it f. When you do it on your calculator, it's usually y1. y1 of theta is the sine of theta. Okay. We said the domain was all reals. You can put any angle in that you want. The range was from -1 to 1. We said it's an odd function. And by the by, remember, I had put these all, let me pull up your class page for a minute. This is I period, yes? Back when we were doing this before the exam, you had this library of functions. And in the library of functions, I had included the sine, the cosine, and the tangent. And called the arctangent with an asterisk. These will be covered in the second semester. We're going to be covering these now, right? So we're doing sine and cosine. And one of the things you should be able to do is to talk about the domain and range. Where are they? They're down here with the little waves somewhere in here. Okay, so there's the sine picture. The sine function's domain is the set of all reals. And the range is -1 to 1. So you have this already in your class. We can talk about increasing, going up, and decreasing. That's all there. The most important thing about this is something called the period. And we're going to find the period today. Symmetric about the origin, right? It is odd. Okay, period. What do we mean by period? There's a lot of periodic phenomena in nature. The sun rises and then sets, and then 24 hours later it rises and then it sets, and then 24 hours later it rises and it sets. The tides rise and fall, and rise and fall, and rise and fall. There's all sorts of cycles that happen in nature, the cycles of the seasons, right? In math, the functions that show this repetitive behavior are the trig functions. That's one of the reasons they were sort of invented, to start to talk intelligently about phenomena that you see. So here's what's called the fundamental period. This is a piece of the wave. And if I could somehow copy that, I think I can do this on here if I'm intelligent enough, and then paste, and put it right there, and then paste it again, oops, paste, and put it right there, and then paste it again, and put it right there. What I'm doing is I'm getting this repetitive pattern over and over and over and over again, right? So this section, if you want, and I can use this section, can actually just be moved and be placed all the way along the line. Now, why is that the case? Well, remember where this thing comes from. It comes from the circle. So let's suppose you were on a Ferris wheel, and this is a goofy Ferris wheel because this is ground level, this is 0, and they built a trench for the bottom of it, right? So we're going to go up in the sky, and we're going to go down below ground, okay? And here's your car. You get on the car right here. What level are you? 0. You're at 0, right? And the Ferris wheel starts to ride. And as you go, how high are you? 1. And you go back to 0. And then you go -1, and then back to 0. That's what this is showing. This wave, it starts at 0. It goes all the way up to 1. And then it comes back down to 0. And then it goes down to -1. And it goes back to 0. And every time you go around, it just repeats over and over again, right? That's that repetitive idea. Now, we don't need the graph now. I'm going to give you some information about it because it helps. This right here is at pi over 2. This is at 1. And you go, what the heck does that mean? That means that this is the theta axis, right? These are angles that we're talking about, and this is the sine of the angle. If the angle is 0, we're at 0. So maybe I can move these along at the same time. That green dot and that green dot mean the same thing. Okay? When the angle goes up to the top of the circle, what angle is that? Don't tell me 90 degrees. Do it in radians. Pi over 2. When the angle is pi over 2, here we are. We're at the top of the wave. Okay? When the angle goes all the way to here, now this is, in geometry class, I think we called this a straight angle. Right? How many degrees? 180 degrees, right? And pi radians. So here, by the way, you know what this number is on the axis right here? You want to take a guess? Pi. Okay. We're on a Ferris wheel. We're going back. Now we're down here. What's the angle as it goes all the way around? How much? 270 degrees. Do it in radians. Say again. 3 pi over 2, right? Because this was 1 pi over 2 up here. This was 2 pi's over 2, right? Or 1 pi. This is 3 pi's over 2. By the way, that's this tick mark right here. 3 pi's over 2. Okay? I'm on the Ferris wheel. I go back up to here. I'm back to ground level. 2 pi or 4 pi's over 2, if we want, right? So here was 1 pi over 2, 2 pi's over 2, 3 pi's over 2. This is, right? So this is 4 pi's over 2. I know that's sort of silly to write 4 pi's over 2. It makes more sense to call it 2 pi. So let's do that, 2 pi. Okay. And then the ride repeats, right? We just do the same thing over again. So we sit there and go, let's go around again. Did anybody get to ride the Ferris wheel at Waterside this summer? It was like $20 or something. It was expensive. The cars were air conditioned, and you could put like 20 people in there at once. And it just went. Anybody ever been to London? Did you ride the Eye? Okay, so those are like big cars. You could put like 60 or 70 people in there. But again, air conditioned. It's all, you get to ride around. That goes a lot higher than the one award. Cool. Did you ride the Eye? You can't go to London and not ride the Eye, right? That's the, for those people that haven't been there, just rent the James Bond movie where they're doing something on the Eye. I don't know. This repetition every 2 pi, this repetition every 2 pi is called the period. So one of the most complicated things when you look in your book, and I do want you to read your book, the author wrote it for a reason. He says the period of the sine function is 2 pi. And this is the way he writes it. The sine of theta plus 2 pi k, now that looks weird, is the same as the sine of theta. And then there's a little subscript down here that says k is any integer. Okay, so, and this talks about the period of the sine function. Where's the reference on this? This is on page, it's the top of page 397. So page 397, when you go through your 397, when you go through your book, page 397, period of the sine function, 2 pi. That's because of that rotation around the circle, 2 pi. And again, you should know that. Remember, if I said, how many degrees is there in a full rotation, you would say, how many degrees? 360. How many radians in a full rotation? 2 pi, and that's when it repeats. Okay, so 2 pi is 1 rotation. Okay, what else do we need? Oh, there were some problems in your book exercise set. Let's look at those just for a second. So one of the problems I'm going to assign is number 19. It says find the cosine of 33 pi over 4, and you have no calculator. And you go, oh, mamma mia. Okay, how many pi fourths? This is sort of a weird way of writing it. How many pi fourths are there in 1 rotation? Question mark. Okay, so here's 1 pi over 4 right here, right? That's 1 pi over 4. 1 pi over 4. This is 2 pi's over 4. Okay. This is 3 pi's over 4. Remember slicing your calzone into 4 slices? Right? 3 pi over 4. By the way, that was like the previous section's homework. If I said what was the cosine of 3 pi over 4, you simply found 3 pi over 4, you wrote the ordered pair, which was your quiz, and then you looked at the x-coordinate, right? Okay, here's 4 pi, 5 pi, 6 pi, here's 7 pi, here's 8 pi over 4, right? So the answer to this, how many pi's over 4 are there in 1 rotation? 8. That means if I take 8 pi's over 4 away from this, so this is the same as the cosine of 25 pi over 4. I just took 8 pi's away, took away a rotation. Can you take away another rotation? Sure, why not? Because it's periodic. This is the same as the cosine of, take away 8 pi over 4 from 25. 25 take away 8, 17 pi over 4. Take away 8 pi again. No, 17 minus 8 is not 11. 9 pi over 4. Cosine of 9 pi over 4. Take away 8 pi again. Do we know what the cosine of 1 pi over 4 is? You put it on your quiz. Answer? Square root of 2 over 2. Because it was asking for the cosine, right? Ah, yes. Okay. So look at your book. Look at your homework. I'll put it up. It'll say read the section, supplement your notes. I'll give you some homework problems that you can do tonight, right? And then we'll pick this up on Tuesday. Our chapter test is on Wednesday. See you later. Have a good weekend.